All right, page 220 in your textbooks, just 3 questions to answer, and then you also had 3 problems as we were wrapping up section 14.1 and 14.2. The questions, though, from our content we're going to get into today and in the days ahead. Question number 18, how is each of the following defined? The calorie with a capital C, and the BTU. And just define the calorie with the little c for me, if you would. Kendall?
The calorie is the common unit of heat.
It is, but that's not how it's defined. Audrey?
It is the heat required at 1 atm to raise 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius.
Good, there we go. So part 2, let's go back to Kendall. How do we define the calorie with a capital C?
The calorie with a capital C is the energy content in foods.
Okay, we do use it to describe energy content in foods. Again, food equals energy. That's why you must eat to have energy, or get an IV drip. A little awkward to move around, though, that way. Yes, sir? How did you define the calorie?
It is the equivalent of 1 kilocalorie with a little c.
Good, it's a kilocalorie, or 1,000 of the little c calories. And what's the BTU? Third tries the charm. Kendall?
The BTU is the U.S. customary unit of heat.
Okay, it is, but that's not how we define it. Michael?
It raises 1 pound of water from 63 degrees Fahrenheit to 64 degrees Fahrenheit at 1 atm.
There we go. All right, number 19. What's the difference between heat capacity, capital C, and specific heat, little c? Kendall?
The heat capacity is the heat required to raise its temperature by 1 degree, and specific heat is the temperature required to raise the temperature of a unit mass by 1 degree.
There we go. A unit mass, or usually we'd say a single gram, is specific heat, where heat capacity relates to the entire object. Good. Number 21. What substance has a much higher specific heat than any other substance recorded on table 14.2, and what is the specific heat of that substance? Audrey?
The substance that has a much higher specific heat than any other substance in that table is liquid water at 4.18 joules per gram times Celsius.
Very good. Excellent. Water, a higher specific heat than the other things on the list. We'll talk about that in just a little bit. For now, let's go and review some things we talked about. Going back to last week, and we said thermal energy was kind of the topic of discussion. What is thermal energy? Michael?
The transfer of heat from one body to another.
No, heat's the transfer of the thermal energy from one body to another. So what is thermal energy, Kendall? Audrey? Okay, thermal energy is the kinetic energy of an object's atoms and molecules. The kinetic energy these atoms and molecules have is the thermal energy of the water. The thermal energy of your body is the kinetic energy that those atoms and molecules have. So the air around us, its thermal energy is the kinetic energy that the molecules in the air have. The less thermal energy they have, the lower the, what's the measure of thermal energy, class? Temperature. The lower the temperature. So when you say, oh, it's cold outside, what we mean is that the air molecules have low thermal energy compared to what we're used to here in Georgia, right? Cold is a relative term. We just mean lower thermal energy than we're accustomed to. If someone has cold hands, it means that their hands, the blood circulating in their hands isn't doing too good, right? Maybe have you ever noticed when you're sitting still, sitting around the house, watching television, you get cold? But as soon as you get up and your mom's like, get in there and make your bed, clean the dishes, clean the floor, vacuum the house, paint the walls, whatever your mom has you doing, right, just on a routine Saturday. Right, when you get busy doing things, right, your body's moving more, your blood is moving more, and suddenly you don't feel so cold anymore, right? You're giving your body, the atoms and molecules of your body, especially in the bloodstream, more thermal energy. Your muscles are moving, right? Your muscles are contracting and relaxing and extending, things like that. And as they do, they're moving. Higher kinetic energy of those particular atoms and molecules, therefore higher thermal energy, therefore higher body temperature, right? If we recorded your temperature after a 12-minute run, everybody has a fever, right? Nobody gets to come back to school because everybody's got COVID, okay? We don't do that, right? We measure your temperature. Hopefully you've had a nice, calm car ride. Now, theoretically, we're not doing this anymore, obviously, but during COVID, right? If you're like, I don't want to go to school. Well, you could use a hot pad on your forehead. That's cheating, but whatever. Or you could be moving constantly in the car. And the more you're moving, the greater thermal energy your body has. And, so you'd record a higher temperature. But again, what is thermal energy, Michael?
It is the kinetic energy of atoms and molecules.
Good. The kinetic energy of the atoms and molecules in the substance. How do we measure temperature? Class? Don't overthink this now. Thermometer. There you go. You knew that as a 5-year-old. Thermometer is how we measure temperature. And the way it works is the thermal energy transfers from your forehead or under your tongue, or we did the under the armpit thing when you were little. We did the armpit thing. It's better than the other one that you can use when you're really little. Well, anyway, you don't remember those days, and it's good you don't remember those days. How many of you younger sibling, you know what I'm talking about? Yes, okay. Bad days. All right. I do that to little children, I tell you. Anyway, in the ear, there are ear readings as well. I've seen those ones. But anyway, the thermal energy transfers from the one to the other, and as the thermal energy transfers, they attain the same thermal energy. Same with shaking hands with someone. Same with holding onto the water bottle that's a little bit cool because it has a low specific heat, but that's going back to, that's getting ahead of ourselves, right? The energy flows, the thermal energy flows from where there is greater thermal energy to where there is less. You step outside on a cold day without a coat on. The thermal energy transfers from you to the air around you. It warms the tiny little space around you before dissipating and being lost forever. And absorbed by the environment, I should say, the surroundings. And so thermal energy transfers until objects in contact reach the same thermal energy. That's a point known as, class, thermal equilibrium. When the system reaches the same thermal energy throughout, all objects have the same, it's thermal equilibrium. That's the premise of how a thermometer works. What do we call this flow of thermal energy from one body to another, or transfer of thermal energy? That's actually heat. So thermal energy is the energy, the kinetic energy of the atoms and molecules. Heat is the transfer of this thermal energy from one body to another, or the flow of that thermal energy. We're measuring temperature. We had 3 temperature scales. Audrey?
Fahrenheit, Celsius, and Kelvin.
Fahrenheit, Celsius, Kelvin. And which is the main one used in science and really around the world today? Celsius. Do you remember the other name for Celsius that you may hear occasionally? Centigrade. Okay, and Celsius is an awfully nice form temperature scale. Here in the U.S., we stubbornly cling to, even though scientists have ditched it, Fahrenheit. And then there's one that is only used in science, and that last one, of course, class, is Kelvin. Kelvin's special. It's known as a blank scale. What's that word?
Absolute.
An absolute scale. What does that mean, absolute scale, Kendall?
It has the lowest possible temperature.
Not necessarily.
Its lowest temperature is the bottom temperature.
You're close. You're kind of getting the reason why it works. Yeah?
No negatives.
No negatives, right? That's all it means. It means no negatives, right? For instance, Celsius kind of takes here's kind of the benchmark, and if you go lower than that, you're negative. For instance, if we said the benchmark height for a fully grown adult is, say, 5 feet. That's kind of benchmark. Higher than that, we have tall positive heights, and shorter than that, we have negative height. We don't like that. Nobody wants to have a negative height, right? Right? So we say, well, ground level is baseline. You can't be shorter than that. Anything above that is just positive. Everything's positive heights, right? Aren't we thankful that I'm just picking on Kendall now? I had a great time picking on Michael on Friday in pre-cal. You missed it, but it was really good. So anyway, we pick on Audrey too. We just usually pick on her about OCD things, or give her sugar. Either one. They're both fun. Anyway. How did I get off on that? Oh yeah, Kelvin. Yeah, absolute scale. What does absolute mean, class?
No negatives.
No negatives, right? So the lowest temperature then on the Kelvin scale has to be 0, right? Which we call absolute zero. What is this absolute 0 on the Celsius scale? Kendall?
273.15.
Close.
Oh, negative.
Negative 273.15 degrees Celsius. These are equivalent temperatures. It's about negative 458 Fahrenheit. But this is the equality that we need to know. So, but the thing is, Kelvin and Celsius, they go up and down together. We would say that together, class, they are equal interval scales, right? You go up a Kelvin, you go up a degree Celsius, and so on and so forth. So to convert from one to the other, we just add or subtract, class. 273.15, that, right? And we just need to remember which one's going to be the bigger number between the two. Kelvin's always going to be the bigger of the two. Now, Fahrenheit. doesn't have a direct equivalence with Kelvin, but Fahrenheit does have a direct equivalence with Celsius that we can use. What was that conversion if we want Celsius and we have Fahrenheit? I want Celsius. Michael?
9/5.
Other one.
5/9.
Because Celsius is usually smaller numbers.
And Fahrenheit -32.
Good. We're going to start with the Fahrenheit -32 and then take 5/9 of that. The converse would be if we wanted Fahrenheit for some silly reason, we'd multiply 9/5 of the Celsius and then tack on a 32 at the end. We said on the Fahrenheit scale, pure water freezes at 32. That's because the saline solution was supposed to freeze at 0. Pure water freezes at 32. Pure water boils at 212. On the Celsius scale, though, it's happy. Water freezes at 0 and boils at 100. Nice 100-degree difference there. The Celsius and Kelvin scales, when thermometers, when calibrated, are based on a very specific, I say temperature. It's more than just a temperature, but a very specific, what's the word I'm looking for? Reference point. What is that reference point for the Celsius and Kelvin scales, anyone? The triple point of water. Do you remember what the temperature for the triple point is? 0.01 degrees Celsius, but only if we have very low pressure, near vacuum level pressure. Water can exist in all three phases. Fahrenheit just is what it is. Nobody cares anyway. We don't use it in science. From there we talked about this idea that as objects gain thermal energy, right, the atoms and molecules begin to move more, they can't pack in as tightly. So as they gain more thermal energy, of necessity, they must spread outward. Therefore, an object, as it gains thermal energy, must, class, expand. So we talked about thermal expansion. And we said there's 3 factors that affect thermal expansion. And we're about to get to the math part of this. What's one of the factors that affects thermal expansion, Audrey? One of them should be kind of obvious.
The length of, coefficient of,
Okay, that's not the obvious one, but I'll take it. The coefficient of expansion, right? Coefficient of linear expansion specifically, which we represent with the Greek letter alpha. And that's based on the type of material. So that would be the first thing, is what is the material? What kind of substance is it? Different substances expand at different rates because the molecular structures are different. What's another factor?
Change in temperature.
That's the obvious one. The temperature change, right? If you change the temperature a lot, you're going to get more expansion. Change the temperature a little, you're not going to get as much. So the change in temperature as well. And then, Michael, what's the last factor that affects thermal expansion?
Original length.
The original size in general, right? Something that's big is going to be able to expand more. If we heated Michael and we heated Kendall, Michael will expand more than Kendall will. Now, proportionally, it would be the same, but because there's more of him, there's more atoms and molecules to him. When his molecules spread out, since there are already more of them, they'll spread out more than hers will. And so the original size, or if we're talking about linear expansion, a length expansion, which again, length doesn't have to mean this way. A change in height would be a linear expansion, wouldn't it? Because it's one-dimensional. We said that the change in length, or the elongation, is going to equal the alpha, that's the coefficient, times the original length, times the change in temperature. This was the equation we needed for our homework. But we said that not only technically will an object change its length or its height or its primary dimension, but I mean technically the other dimensions change also, right? So we would also have to account in some cases for a change in area. For instance, 2 dimensions, right? So we said we changed the formula just a little bit for change in area. Volunteer, what's the formula look like if we go for an area change instead of a length change? Michael?
2 alpha, a sub rho, change.
There we go. We just double the alpha. Technically, it's a gamma value, but we double the alpha value to get the area change. And then we said, well, what if we want to change all 3 dimensions? Class, that would be a change in volume, change in how much something holds. And one of you ladies take this one. All right, Audrey?
3 alpha, the sub times change in temperature.
There we go, 3 alpha. Technically beta, but I mean, it's triple the alpha value times the original volume times the delta T. Now, I did say the original length or area or volume, the original thing that we're given, we're going to look to that for 2 different things in our answer. First of all, Kendall, we're going to use it to get our sig figs, but we're also going to use it for our units. We don't have to change units to anything special. Whatever units they give you, keep them. Whatever sig figs they give you in the original, use that. Again, the alpha value you're going to get from a chart, and which again, if you needed more alpha values, you could look them up online. I mean, there's a huge list of coefficients of expansion. How do I find change in temperature? Final minus initial, right? Final temperature minus initial temperature, but these temperatures, class, must be in Celsius. So these have got to be in degrees Celsius because the alpha value refers to Celsius. At least the ones we're using. Now again, you may take a science class, a physics class in college, their alpha values may refer to Kelvin. Well, if that's the case, you would need Kelvin temperatures. We're using ones that are based on Celsius, so we're going to use Celsius temperature change. We said that's for solid expansion primarily, but do liquids and gases also expand when heated? Yeah, of course they do. We talked about gases. That was Charles's law, right? Volume and temperature directly related. You heat a gas, it spreads out. Heat the balloon, unless it pops, it'll get bigger, right? Cool the balloon, it'll shrink. Liquids the same way. They expand when they get heated. They contract when they cool. There's only one small exception to that. What is the only known exception to this concept of thermal expansion? Kendall, do you remember? No idea? Michael? Ice. Water as it freezes. And again, it's not, water will expand when heated, water will contract when cooled, ice will contract when cooled. But as it's freezing, in that freezing range, water changes its structure. That makes it less dense. Why is that important? Back to Kendall, from what we talked about on Friday. Why is it important that as water freezes, it expands, going into that crystalline structure? Audrey?
Is that all the fishies and...
I knew she was going to say it. I was going to say for the fishies. I was waiting for that word. I knew it. Good. You didn't let me down. Thank you.
They don't die.
Why is it that, why does water expanding like that make fishies not die?
The ice sits on the top and it doesn't crush all of them below.
Yeah, the ice as it freezes stays at the top instead of becoming more dense as it contracts and falling. It expands, making it less dense, and it stays on the top. You ever put something in the freezer, a bottle of water or something, and it exploded because it tried to expand beyond what the container allowed? My friend, shout out to Jeremy, from high school and college, we were working at the same Christian camp. I was running the camp store, and he went to the vending machine and got a can of cherry Coke. Right as he got his cherry Coke, before he could enjoy it, the counselors got called to go take their kids somewhere. It's like, oh man. So I'm like, hey, can I put this in your ice cream freezer till I get back? No big deal, put it in the ice cream freezer. Well, the problem was he didn't come back. The next morning, I'm restocking the ice cream, and what is that sweet smell? Oh, that's weird, whatever. Stocking the ice cream. Well, later I had to pull one of the racks out to get some of my back stock underneath, and there's cherry Coke frozen all over the place. And again, primarily water in Coke, right? It's carbonated, but it's water in there, and the water expanded, the can couldn't handle it, boom, and expands when it freezes. Thank you. That was not beneficial to aquatic life. That just made more work for me. But anyway, one example of this we'll show here is I've got a ball here on the end of a rod. I've got a ring here, and you notice the ball and ring, kind of like a finger fitting in the ring. It fits just fine, right? But what we can do is we can heat the ball. There we go. All right, we'll edit what we need to. All right, so we've got this ball. It fits neatly inside the ring. But if I just leave the ball in the flame for just a few seconds, what's happening to the atoms and molecules, class? They're speeding up. They're having to move faster. They're gaining kinetic energy. So what's happening to the ball, even though you can't really tell by looking at it? It's getting bigger. You can't tell by looking that it's bigger until you try to fit it in there, and it doesn't fit. Kendall, without touching this to your hair, because we don't want to melt anything, would you confirm, yes, Mr. Nessie's not just being stupid, it really doesn't fit. Now, can you get it back out? There we go. All right, and now Audrey, no catching yourself on fire,
Okay.
like the chemistry lab last year.
Okay.
Okay, you confirm it doesn't fit, it's not just me trying to pretend. Okay. Michael, you can actually come up here. Come on up, come on up. You be my guinea pig here. All right, and so, just reheat it a little bit extra there in case it had cooled a little. All right, so he tries to fit it in. It is not fitting. Okay, but Michael, put the ring in there now. And remember I told you that when you heat a ring, the ring is going to expand in all directions. The hole has to expand as well because the inner surface has to expand outward. The outer surface expands outward. And so if we heat the ring, now the ring is also expanding. Michael, see if we can fit that ball through now. Okay, so now that both of them have been heated, we can expand them through. Now, if we allow this to cool and we reheat the ball a little bit more, again, just expanding a little bit, you can't tell a visible difference, can you? Small, imperceptible changes as we talked about last time, but now got it through still. Okay, so we didn't heat it. Let's do this. Let's heat the ring. And now it comes back apart. All right, so stay. So anyway, just a fun experiment. It's simple there, and without burning ourselves, right? And supposedly, I think I'm supposed to wear eye protection, a lab apron, but I'm way too lazy to get all that stuff out. And so I haven't caught myself on fire yet. This is my 12th year doing this, so banking on safety, safety first. All right, anyway, but a simple demonstration there. Let's take a look at the homework problems now. Problems 7, 8, and 11. It used these equations for thermal expansion. We're there on page 221. Read problem 7 for us, if you would, Kendall.
A pine wood meter stick is 100 centimeters long when the temperature is 32 degrees Fahrenheit. What is its length when the temperature is 77 degrees Fahrenheit?
All right, right off the bat, I see some numbers I can't use. Class? Can't use Fahrenheit, right? So it says the original length, L sub O, is the 100.00 centimeters? Yes. But we're going to have to change the initial temperature from 32 degrees Fahrenheit, class, to, what is it?
0 degrees.
We can do that in our head, right? 0 degrees Celsius. The final temperature, it said was 77 Fahrenheit. We're going to have to subtract 32 and take 5/9 of that to get 25 degrees Celsius. All right, so therefore, what is the change in temperature, class? Positive or negative 25? Positive. The temperature went up to 25. That's a positive change. Positive 25 degrees Celsius. Now, the last thing we're missing, we've accounted for the original length. We've accounted for the temperature change. We also need to account for the type of material. It says the meter stick is made out of pine wood. So we had to look back at page, I believe it's 211, and look up the alpha value for pine. What is that value? 5 E negative 6, and it's just per degree Celsius. So that the degree Celsiuses will cancel here, and then we'll be left with centimeters. And did it ask for the new length, or does it ask for the change in length? It says find its length, meaning its new length, correct? So we need to find the new length of this thing, but that starts by finding change in length. And again, change in length is simply the alpha times the original length times the change in temperature. So we're going to multiply all three values together. 5e negative 6 times 25 times 100. And what is the elongation of the meter stick, class?
0.0125.
An 80th of a centimeter. That's nothing, right? You would not be able to tell a perceptible change if the meter stick was made in freezing conditions and was brought into a warm classroom, right? However, as for the new length, how would I find the new length?
Add it to the original.
Add this plus the original length, and that'll give you 100.0125, but rounding the answer off to that, well, technically you could say at this point it's place value more than anything, we would get 100.01 centimeters. By the way, technically that would mean all your readings are off by just that tiniest little bit, right? Again, an 80th of a centimeter. So it's not much, an 1/8 of a millimeter off. It's pretty much nothing, right? But they would be off that little bit. We'd call that systematic error, wouldn't we? Caused by a slightly faulty instrument. Again, that's the benefit, though, of using a pine meter stick. They're not going to expand or contract much. Metal would contract and expand a little bit more. We had a lab that I did in college. We had pressure chambers we could slide different metal rods into, and we could heat them up in these pressure chambers, take them out and measure the temperature change. And there it was a little bit more easy to read the temperature changes because the metal expanded and we had them heated up. Kind of like, imagine one of these, but you could heat the entire length of the stick at once. Anyway, cool stuff you can do if you take a college physics class. Anyway, I'm not going there. All right, number 8. Go and read that one for us, if you would, Audrey.
The Eiffel Tower in Paris is 984 feet tall and is made of iron. Assume this measurement is exact. Calculate its change in height when the temperature changes from 0 degrees Celsius to 40 degrees Celsius.
All right, so we're assuming that the Eiffel Tower is measured 984 feet tall. When it's 0 degrees outside, it's 984 feet. And then one particularly hot day, it's 40 degrees Celsius. So over time, as the temperature has increased, so is the Eiffel Tower. No one's really noticed. Maybe there's been a little creaking and groaning. How many have been in the auditorium and you've heard the creaking and groaning of the rafters and you're like, oh no, the whole place is going to fall in. And a thermal expansion, right? Starts out really cold especially, and then as the day warms up, the sunlight beating down upon the roof and things begin to expand just a little bit. It's okay. It's not going to crash. At least it hasn't yet. And so statistically, we feel pretty good about this. So now, again, our original length or original height, right? 984 feet. They gave us 3 sig figs. They gave us feet. Let's roll with it. They give us a change in temperature of 40 degrees Celsius. And the alpha value, what's it going to be for this problem?
11.
Iron has an alpha value of 11, E negative 6 per degree Celsius. Again, these units will cancel away. Again, we just multiply the 3 numbers together. And what did we get for the change in length? Anyone? 0.43296. Again, that's 5 sig figs. We're going to cut it at 3, except it didn't ask for the change in length, did it? Oh. Yes, it did. It did. It said by the change in height. Perfect. Okay. That makes me feel better. I'm like, man, but if you do that, you're not going to notice a perceptible difference. That's really kind of sad. No, we didn't want change in length. We're going to round it off to the 3 sig figs, and we're going to say feet. So, class? 0.433 feet. And if you wanted to multiply that by 12, it would give you 5.19, about 5 1/5 inches. Okay, 5.2 inches height change. So it's even taller when it's hot outside. Yeah. Is anybody going to notice 5 inches? No. Not when it's 984 feet to begin with. Less than half a foot change. Nobody even notices. Questions on that one? How many got that answer? All right. And numeral 11-0, read that if you would for us, Michael.
The iron rim of a wagon wheel has an internal diameter of 1.5 meters when the temperature is 120 degrees Celsius. What is its internal diameter when the temperature is lowered to 20 degrees Celsius?
All right, so imagine going back to the old days. Got the blacksmith there. He's making this iron rim of the wagon wheel, and he's forging it so it's really, really hot metal, because so that way it's malleable, right? It's hotter than this would be. He's forging it into the proper shape, the proper size, and when he forges it, the internal diameter is exactly 1.5 meters. But of course, it's not going to stay in the furnace. And what's going to happen when he takes it out of the furnace and it begins to cool to the outdoor temperature? It's going to contract a little bit, isn't it? It's going to change its diameter. Again, that's a one-dimensional measure. Often when we think diameter, we think of how we can use it to find area. But it's not looking for a change in area. It's just looking for a length change still. So we're still going to say that the change in length is equal to alpha. Now it's iron again, right? So once again, the alpha is 11 E negative 6 per degree Celsius. Again, that's the type of material. The original diameter here is the 1.500 meters. What's the temperature change? In the furnace, 120 degrees Celsius, down to 20, which is about 60, 70 degrees. Negative 100. Now, what's this going to do? Well, it's going to give us a negative change in length, meaning it shrinks. So we multiply the numbers together, and we get a change in length of negative 0.00165 meters. Did we get that change in length? But it didn't ask for the change in length. It asked for the internal diameter, the new internal diameter, if you will. We're still going to add this to the original. But because it's a negative, when we add it to 1.500, it's going to produce a smaller number, isn't it? So we added that to the 1.5 and got
1.4983.
1.49835. Now again, we're going to cut it off at the 4th sig fig, or if you will, the thousandths place, and we'll say 1.498 meters. Did it shrink much? 2 millimeters. That's not much. Not even quite 2 millimeters, but rounded around 2 millimeters of shrinking. Big deal. It'll be fine. All right, questions on that? All right, I want you to do problem number 6. Problem number 6. Let's also do 10 and 12 will give you a volume change. So problem 6, 10, and 12. There at your seats. All right, looks like we're finished on number 6. The original length is 5 centimeters. The change in temperature class is
10 degrees.
positive 10 degrees Celsius. It's made of silver. What was the alpha value for silver class?
18 -6.
18e negative 6?
Mhm.
And so she got a change of 0.0009 centimeters, but you have to add that on to the 5.00 centimeters to find its new length. And when you round, you get what answer, Michael?
5.001.
5.001 centimeters. Can we get that answer? Excellent. Number 10. Again, we're not looking at area here because it's only looking at a single dimension, and that is diameter. So we're still going with change in length here. The temperature change is
30.
good, 30 degrees Celsius. And we're looking only at the diameter of the
The whole.
hole, right? So ignore the 10 centimeter diameter. We're not using that number, nor are we using it sig figs. The number we're looking at is the 5.0000 centimeters, right? So we're taking that times the 30, which is the change in temperature, times the, what's Gould's coefficient of expansion?
14.
And again, it says calculate the new diameter, so we're going to take the change, 0.0021, add that on to the 5.0000, and we get what for our answer, Kendall?
5.0021.
Centimeters. It is correct. 5.0021 centimeters is the new diameter of the hole. Questions on number 10? How did you get that answer? All right, and number 12. Now this one's a little bit different because they give us two substances we have to compare. Read number 12 for us, Audrey.
The storage tank made of sheet iron holds 4 cubic meters of alcohol, where the beta is 1.12 E negative 3 degrees Celsius. When the temperature is negative 10 degrees Celsius, how much alcohol will spill out of the temperature is raised to 40 degrees Celsius?
Now, we presume this is not an alcohol that you would drink. This is like an alcohol used in sanitizer, right, to fight COVID-19. All right, and so anyway, we've got two substances. We have the tank and with the alcohol in the tank. Now, assuming that the tank is completely full, what's the volume of the tank? 4 cubic meters. And if that's the volume of the tank, then what's the volume of alcohol? 4 cubic meters. Now it tells us that the tank is made out of iron, but since we're looking at the volume of the tank, we need to triple the alpha value. Iron, remember, is 11e negative 6 for linear expansion, but this is volume expansion. Triple 11e negative 6,
33.
and we get a beta value of 33 e negative 6 per degree Celsius. It tells us that alcohol has a volume of expansion of 1.12 e negative 3 per degree Celsius. By the way, notice alcohol is a much higher value. E negative 3 is 1,000 times, really in this case, 33,000 times smaller than this value, correct? So the alcohol is going to expand a lot more rapidly. And then, of course, we have the change in temperature. What is the change in temperature here, class? To go from negative 10 up to 40 is a change of 50 degrees Celsius, and that's going to be true for both of these. So what we need to find is what's the change in volume of the tank, how much does the tank expand, because then it can hold more alcohol, but how much does the alcohol expand? And of course, we're going to assume it will expand more greatly. Let's start with the iron tank, if you didn't already do this. What is the change in volume of the iron tank? 0.0066 cubic meters. It has expanded to allow more space. At your seats now, find the change in the volume of the alcohol. 0.224 cubic meters, right? That expansion is greater than this expansion. The difference, right? This is almost 1/4 of a cubic meter. This is less than 1/100th of a cubic meter of expansion. The difference between the changes in volume tells you how much alcohol will spill out of the tank. So we simply, yes, sir?
It's the volume of alcohol. Do we have to triple it or no?
No, they actually gave us beta. They gave us alpha on the chart, remember, so we had to triple it. They gave us the beta, so we didn't have to triple anything. Does that make sense? All right. So you would have had a
4032.
bigger something there. Yeah. All right. So when we subtract what do we get for the change in volume that spills, or the amount of volume that spills out? Anyone? 0.2174. Let's see, we're going to go off the volume, original volume here for sig figs. It's 3 sig figs, so we'll say 0.217. What was the unit? Cubic meters. They gave us cubic meters, so we're going to roll with cubic meters. 0.217 cubic meters is how much alcohol will spill out. Questions on this problem? A little bit next level, right? Because you had to compare two different things. Any questions on thermal expansion? All right. Well, I'll tell you what, we are not going to get into the next material after all. I'm going to go and give you your homework, but we will go and take the quiz while this is fresh in your minds. So we're going to go and jot down the homework, and then we'll prepare for a quiz. I need you to read over pages 213 to 217. Read over pages 213 to 217, and just 3 questions for homework tonight. Page 221. Answer questions 23, 24, and 26. 23, 24, and 26. All right, we're going to prepare for a quiz. Clean sheet of paper, pencil, and calculator. Clean sheet of paper, pencil, calculator, everything else away. First and last name at the top of your paper, along with today's date, which is 1/30/23. 1/30/23 today's date. First and last name, 1/30/23 today's date. This is quiz 18. Quiz 18. Let's take the quiz together, and then once you get started, we'll end the video after I've gone over the directions. First section, numbers 1 through 9, completion. Write whatever needs to go in the blank to finish it off. Notice number 2 is going to require 2 words. Number 3 will require more than a single word. You're writing out some formulas. You're naming some different points. Okay, so there's your 1 through 9. Number 10, list out 3 things. And then for numbers 11, 12, and 13, problem solving. Notice number 12 kind of builds on number 11. So number 12 builds on number 11. And then there's a bonus question for you. See what you remember from a couple lessons back. All right, you may begin.